Okay, in this lecture we're going to move on to the second part of the course. The first part focused on supervised learning, and in this lecture we're going to move on to something called unsupervised learning. So let's step back and think about the framework of supervised learning that we've been focusing on exclusively thus far. So we had pairs of data, an x and a corresponding y, where x was an input and y was an output. And we wanted to learn some sort of a function, f, such that we can accurately predict the output as a function of the input. So we predict yi to be approximately equal to the function of xi. Then the reason why we learn this function is when we get new data, we get a new x naught. We don't know what the corresponding y naught is going to be. We don't know what the response is or what class x naught belongs to, and so we use the function that we learned on the training data to predict the corresponding output y naught for the input x naught. We talked about a few different motivations, one of which is probabilistic motivation. So this is where we think of x and y as random variables with a joint distribution like this. So this is some true underlying distribution that we don't get to observe that nature is using to generate these labeled pairs of x and y. And then we thought of supervised learning as trying to learn the conditional distribution of the probability of y given x. So there's some joint distribution, but we get to see some pairs from this joint distribution. But then we want to learn the conditional distribution so that we can predict y given x. And we saw how this could be done directly or indirectly. Directly was where we directly define this conditional distribution on the label or the output given an input, for example, with the logistic regression. Or indirectly using the Bayes rule, where we could use a Bayes classifier and say that that we were going to predict y given x to be the argmax of the class conditional distribution of x times a prior probability on the label. So here's where we used Bayes' rule to turn the conditional distribution on y given x into a conditional distribution on x given y times a prior on y. And so this is a very general technique. So I mentioned this to give some motivation, some context for what unsupervised learning is trying to do. We see that the Bayes classifier factorizes this joint likelihood into the conditional probability of x given y times a probability on y. Equivalently, we can use exactly the same rules of probability to say that the joint likelihood of both x and y is the conditional likelihood of y given x times a prior on x. So in a sense, with supervised learning, we either focused on this term or we focused on learning both of these terms together. Now you can think of what we're going to do is to develop models and define models that allow us just to define some sort of a distribution on x. Or you could even think learning some class conditional distribution, which we had to define. We assumed that this was a simple multivariate Gaussian previously, but maybe there are more complex distributions that are better suited to the data we're modeling that we might want to learn. So what should these distributions on the data be? What should these distributions on x be? So that's the focus of unsupervised learning in a sense. And even though I'm framing it as kind of a special case of supervised learning, where I'm almost implying that there's some underlying supervised task we want to perform, there often isn't one. Often what we really care about is understanding what information is in the data that we have, and that can boil down to, in the probabilistic sense, learning some distribution on our data that captures its underlying qualities. So that leads us to the unsupervised framework. And so this is what we're going to be focusing on for most of the second half of this course. So we have now data given to us where we simply have these x's x1 through xn, where each x is in some space. For example, x could be in Rd. Now we're going to define some model, either probabilistic or non-probabilistic, on x only. And the goal that we are now going to have is to learn through this model the structure underlying this data set. So learn what's going on with this data set, learn what are the statistical properties of this data set, et cetera, et cetera. And it's going to be less clear what exactly the measure of quality is. With supervised learning, it was clear that we were trying to predict something at the end of the day. And so we could use, as a measure of performance, how well we're able to make predictions on new data. Now, we're trying to do other things like learn the underlying characteristics of the data, also possibly make predictions, but it's going to be less clear what exactly the quality measure is going to be. Here's an overview of the second half of the course. This is going to be most of the second half, not entirely the second half, but we're going to focus on three types of unsupervised learning models. The first thing we're going to focus on in the first few lectures are clustering models. So the goal with these types of models is to take our data x1 through xn and to partition them into groups. And the applications for this include image segmentation, data quantization. Also, it's often used as a pre-processing step for other models. So it's a very useful technique that has many different applications. Then we're going to discuss matrix factorization methods. And this is where we're going to try to learn some underlying dot product representation of our data. And these are going to be useful for things like preference modeling, movie prediction, movie rating prediction, topic modeling, so taking text documents and learning what are the underlying themes in these documents and so on. And then finally, the last main set of models we're going to discuss are sequential models. And so these are models where there's some sort of a sequential assumption. Either the data is sequential in nature, or we're going to use some sort of a sequential way of representing the data. So we'll see an example of how to rank objects in pairwise comparisons, and target tracking would be another application. And as is going to be evident, the division between supervised and unsupervised is not clear-cut. What sometimes can be viewed as an unsupervised technique, given a different perspective, just viewing the data in a different light, will suddenly become a supervised technique. So the division is kind of rough, but the techniques are still very useful for a variety of things, and so don't necessarily think that the techniques we're discussing now are going to be completely useless for supervised problems and vice versa.